All right, let's continue on. In this lecture video, we're going to look at a formal hypothesis test for lack of fit of a regression model. Now we're going to start out by first looking at the lack of fit test for a simple linear regression model. You'll remember that the general form of the simple linear regression model has one explanatory variable, and so the model looks like, as it's given here on the slide, the response variable y equal to beta 0 plus beta 1 times the explanatory variable x plus epsilon. So that's the general form of the simple linear regression model that we're looking at. And we have this same model for each experimental unit or subject in the data set. The only difference is the data that they have corresponding to them. So they have their own y value and their own x value. And so when we're processing that kind of data in the context of a regression analysis, we need to distinguish between the models for the different experimental units. And we do that, typically do that by using a single subscript. So in deriving estimators and presenting their formulas, we typically work with a singly subscripted version of the model represented here, y sub I equal to beta 0 plus beta 1 times x sub I plus epsilon sub I, where the index I uniquely identifies each of the n experimental units or subjects in the data set and their corresponding data. So the corresponding data in the context of a simple linear regression would be x1, y1, x2, y2, and so forth up to xn, yn, these data pairs belonging to each individual experimental unit. Now, this index has a one-to-one relationship with any single attribute which uniquely identifies an observation, such as the row in the data set that the observation occupies, or perhaps a unique identification number. So for example, if the experimental units are people, we might use their social security number as that unique identification number. And so we would have an index I that is in a one-to-one correspondence with that identification number. If the experimental unit was a zip code area, then zip code could be used in that way. So we would have a single index, I, that is in a one-to-one correspondence with zip code. But the bottom line and the point of this slide is that the usual notation, the notation that you're used to seeing, looks like this. We have a single subscript on y, the response, and on x, the explanatory variable, as well as the error term, because we have an error term for each individual subject. Now, there are other ways that experimental units can be uniquely identified in a model. Suppose that there are m distinct values of the explanatory variable x, where m is strictly less than the sample size n. Now, if this is the case, that would imply that at least one of the x values is duplicated in the data set. In other words, what that would mean is that for at least one level of x, there are at least two experimental units possessing the same value for their explanatory variable. Now, we can represent the set of distinct x values in the following way. And so we have x1, x2, and so forth up to x sub m. All right, again, m is the number of distinct values of the explanatory variable x. And so in this situation, x1 is not necessarily the value of x corresponding to experimental unit 1. x2 is not necessarily the value of the experimental or the explanatory variable for experimental unit 2 and so forth. These are the single subscript here corresponds to an index that is identifying the distinct values in the data set. And so, for example, we might sort the data set according to the values in the explanatory variables. And so once we do that sort, then x1 could represent the smallest value of x in the data set, x2 the next smallest value, and so forth. Now, each experimental unit in this situation can then be uniquely identified by the combination of two indices. First, an index of the level of x it possesses, and then the second index would be an additional index indicating which of the experimental units possessing that level of x in the observation is in the data set. And so let's take a look and see what this looks like. In particular, with this alternate method of subscripting, the model would look like this. Y sub ij equal to beta 0 plus beta 1 times x sub I plus epsilon sub ij. Here, again, I is the index that indicates which of the values of x we're talking about. And then j goes from 1 up to n sub I, where n sub I is the number of observations possessing x sub I as the value of its explanatory variable. And so y sub ij is the observed response for the jth experimental unit possessing the ith unique value of the explanatory variable x. Again, x sub I is the ith unique value of the explanatory variable x. And then epsilon sub ij is the error term for the jth experimental unit possessing the ith unique value of the explanatory variable x. So this is it's an alternative method of subscripting, but it's useful in the context in developing a test for lack of fit. Now, let's look at how we would denote the sample mean and the predicted value of the response under this alternate subscripting. And so using this method of double subscripting in the model to identify observations, the sample mean response, the sample mean of the y values for observations possessing the ith unique value of the explanatory variable x would be given by y bar sub I. That would be 1 over n sub I times the sum, I going from 1 up to n sub I. Actually, that would be, we would have a j here. All right, so I need to fix that in my in the note here. So there I've got that index of summation fixed. So again, y bar sub I, okay, that is the sample mean of the response, sample mean response for observations possessing the ith unique value of the explanatory variable x. That is 1 over n sub I times the sum, j going from 1 up to n sub I of the y sub ij's. The predicted value of the response for observations possessing the ith unique value of the explanatory variable x, y hat sub ij equal to beta 0 hat plus beta 1 hat times x sub I. Now notice that this quantity beta 0 hat plus beta 1 hat times x sub I does not involve the subscript j. And so because of that, we can drop the subscript off of this notation and just call this or denote this y sub I, y hat sub I. So again, we have the sample mean response for observations possessing the ith unique value of the explanatory variable x. And we have notation here, y hat sub I, for the predicted value of the response for observations possessing the ith unique value of x. Okay, then we can take that notation for the sample mean response at each level of I, or at each level of x, and the predicted values of the response for each value of x. We can take that and come up with a partitioning of the error sum of squares, a partitioning of SSE. So using this method of double subscripting to identify observations, the error sum of squares, or SSE, can be decomposed in the following way. And so the sum of squares error, because we're using double subscripting, we have a double sum here. So here we have the sum I going from 1 up to m, I going from 1 up to the number of distinct values of x. And then for each of those values of I, j goes from 1 up to n sub I. And we would have the square of the difference between y sub ij minus y hat sub I. Now, I've left out a few steps here, but it turns out that we get this decomposition given here. All right, and so you can take a look at this and see what these represent. I've got two representations of this decomposition. And ultimately, though, we're going to call this decomposition the sum of squares underscore PE plus the sum of squares underscore LOF. Okay, now let me just point out here that in the second decomposition or form of the decomposition, we've rewritten this inner summation as n sub I minus 1 times s sub I squared. Now, in that expression, the s sub I squared is the sample variance of the response variable for the observations possessing the ith unique value of the explanatory variable x. So that's what that represents. Now, SS sub PE, this is called the sum of squares due to pure error, and the SS LOF is called the sum of squares due to lack of fit. Now, recall that for the simple linear regression model, the sum of squares error is based on a number of degrees of freedom equal to n minus 2. And that 2, you'll recall, for the simple linear regression, or because we're dealing with the simple linear regression model, we have n minus 2, and 2 is the number of beta parameters in the model, right? We have we have two beta parameters, beta 0 and beta 1, and those two parameters have to be estimated. And so in estimating those, we lose 2 degrees of freedom for error. All right, and so that's why in the simple linear regression model, the degrees of freedom for error are n minus 2. Now, when there are duplicate x values, these degrees of freedom can be partitioned, just like the sum of squares can be partitioned into the sum of squares for pure error and the sum of squares for lack of fit. The degrees of freedom for error can be partitioned into the sum of the degrees of freedom for pure error and the sum of squares for lack of fit. And it turns out that the degrees of freedom for pure error are n minus m, and n being the total sample size, and m, you'll recall, is the number of unique values or distinct values of the explanatory variable x. And then the degrees of freedom associated with lack of fit is m minus 2. And you'll see, again, that the sum of those two values is n minus 2. And you can see here that once we we can use these formulas to get the degrees of freedom, but if we already have the degrees of freedom for error and we calculate the degrees of freedom for pure error, we can just get the degrees of freedom for lack of fit by subtraction if we needed to. But these formulas are both very simple. We can apply them directly. Now let's talk about the mean squares for pure error and the mean square for lack of fit. So the mean squares associated with pure error and lack of fit, as you would expect, are obtained by dividing their sum of squares by their corresponding degrees of freedom. And so the mean square for pure error is equal to the sum of squares pure error divided by the degrees of freedom for pure error. And so SS sub PE divided by n minus m. And the mean squares for lack of fit, likewise, is obtained by dividing its sum of squares by the corresponding degrees of freedom. Now let's talk about the behavior of these two mean squares. An important characteristic of the mean squares for pure error is that it is always an unbiased estimator of the error variance which is denoted by sigma squared. And this is regardless of whether the specified form of the model is correct. So it doesn't matter whether the specified form of the model is correct. The mean squares for pure error will always be an unbiased estimator of the error variance, because the calculation of the sum of squares pure error does not depend on the model. It only depends on the mean of the response at given values of the explanatory variable where there is replication. So it's model independent, and that's why it's always going to be an unbiased estimator of the error variance. Now, on the other hand, it can be shown that the mean squares for lack of fit will be an unbiased estimator of sigma squared if and only if the specified form of the model is correct. So in the current context, the mean squares for lack of fit will be an unbiased estimator of sigma squared if and only if the simple linear regression model accurately reflects the relationship between the response variable and the explanatory variable. If the specified model is not correct, so for example, in the current context, if the correct model is of higher order than just a straight line relationship, then the mean squares for lack of fit will not be an unbiased estimator of sigma squared. It will actually be estimating something that is greater than sigma squared. So again, the mean squares for pure error is always an unbiased estimator of sigma squared, whereas the mean squares for lack of fit is an unbiased estimator of sigma squared if and only if the specified model is correct. Now, this implies that if the specified form of the model is correct, then the mean squares for pure error and the mean squares for lack of fit will be estimating the same quantity, sigma squared. Because they're random variables, they would not typically be equal, probably almost never equal. But again, if the specified form of the model is correct, they're at least estimating the same quantity. And because of that, they would tend to take on similar values. Now, if the specified form of the model is not correct, then the mean squares for lack of fit will tend to be larger than the mean squares for pure error. And so if we construct the ratio, the mean squares for lack of fit over the mean squares for pure error, that ratio will tend to take on values close to 1 if the specified model is correct, but it'll tend to take on values that are greater than 1, and perhaps even much greater than 1, when the specified model is not correct. And so large values of this ratio are what we're going to be looking for to indicate to us that the specified model is not correct. But the question is, how large does that ratio have to be in order for us to conclude that the specified model is not correct? Well, that requires us to know something about the sampling distribution of this ratio. And in particular, for the purpose of coming up with a cutoff point or a critical point for the test, we would have to know the sampling distribution of this ratio under the conditions of the null hypothesis. Now, the sum of squares for pure error and the sum of squares for lack of fit partition that sum of squares for error. And because of that, the mean squares for pure error and the mean square for lack of fit are uncorrelated. And because they are uncorrelated, if the model error terms are normally distributed, then the mean square for pure error and the mean square for lack of fit are stochastically independent as well. And so because of that, it follows that this ratio, and this is a random variable, and we're going to call this F underscore or subscripted LOF. This random variable varies according to an F distribution with numerator degrees of freedom equal to m minus 2 and denominator degrees of freedom equal to n minus m. And so, and again, this is contingent on the model being correct. And so I probably ought to include that in the slide to make that clear. Okay, so I've adjusted the slide a little bit to make sure that this is very clearly stated. And so from this, it follows that if the specified form of the model is correct, then this random variable, which we're going to call an F value, F for lack of fit, varies according to an F distribution with M minus 2 numerator degrees of freedom and N minus M denominator degrees of freedom. Okay, so this leads us then to the following formal hypothesis test for determining whether there's lack of fit. The null hypothesis is that the specified form of the model is correct. The alternative hypothesis is the opposite of that the specified form of the model is not correct. The test statistic is this ratio, the F statistic for lack of fit is equal to the mean square for lack of fit divided by the mean squared for pure error. The decision rule, the rejection rule, is to reject the null hypothesis if the F statistic for lack of fit exceeds the upper alpha percentage point of an F distribution with M minus 2 degrees of freedom, M minus 2 numerator degrees of freedom, and N minus M denominator degrees of freedom. Now, an assumption that underlies this testing procedure is that the error terms do in fact have constant variance, sigma squared. And you'll recall that this is one of the standard assumptions in regression analysis or in a regression model. And so if there's evidence, for example, in looking at the residual plots, that the variance depends on the value of the explanatory variables in some way, that the variance is not constant, then this procedure is really not going to be applicable, because this formal test for lack of fit does assume, or is based on the assumption, that the error terms have constant variance. Okay, now let's generalize this, and let's look at the lack of fit test for a multiple regression model. And so recall that for the multiple regression model, the sum of squares error is based on N minus P degrees of freedom, where P is the number of beta parameters. So this is the same form as it was for the simple linear regression model, the only difference being here that here we don't know beforehand, or at least in general beforehand, the number of beta parameters. We know in the simple linear regression model, we've got P equal to 2 beta parameters, and so we can plug that in. But in this case, this is a general framework, and so we have to leave that as P. Now, again, when there are duplicate explanatory vectors in this case, because again, when we have a multiple regression model, we don't have just a single explanatory variable, we have a vector of explanatory variables, and I'm denoting these by, number one, I'm denoting the vector by bold X, and then the explanatory variables that comprise that vector, I'm denoting x1, x2, and so forth up to x sub k. So as long as we've got duplicate explanatory vectors, then these degrees of freedom, n minus p, can be partitioned again into degrees of freedom associated with pure error and degrees of freedom associated with lack of fit. All right, and those would correspond to the degrees of freedom associated with the sum of squares for pure error and the sum of squares for lack of fit, respectively. And so the degrees of freedom for pure error would be n minus m, and the degrees of freedom associated with the lack of fit would be m minus p. All right, and then again, we would obtain the mean squares for pure error and the mean squares for lack of fit by dividing the sum of squares for pure error and lack of fit by their corresponding degrees of freedom. So that's really the only difference. We're just, we have to calculate the degrees of freedom associated with the sum of squares for lack of fit and divide that into the sum of squares for lack of fit to get the mean squares. Now, as in the simple linear regression case, the mean squares for pure error is always an unbiased estimator of the error variance, regardless of whether the specified form of the model is correct. And again, the reason for that is that this estimate is not in any way dependent on the form of the model. It is a model-independent estimate of the error variance. On the other hand, the mean squares for lack of fit will be an unbiased estimator of sigma squared when and only when the specified form of the model is correct. If the specified form of the model is not correct, then the mean squares for lack of fit will be estimating something that is greater than sigma squared. Okay, and so that implies then that if the specified form of the model is correct, then the mean squares for pure error and the mean squares for lack of fit will be estimating the same quantity, sigma squared, and hence they will tend to take on similar values. If the specified form of the model is not correct, however, the mean squares for lack of fit will tend to take on values greater than the mean squares for pure error. And so because of these two results, that ratio will tend to take on values close to 1 when the specified form of the model is correct, but it would tend to take on values greater than 1, and perhaps even much greater than 1 when the specified form of the model is not correct. Okay, and so again, what we're looking for here in order to conclude that there's a lack of fit in the model or that the model is not correct, we're looking for large values of that ratio. And again, in order to draw that conclusion formally, we would have to come up with a critical point for the test, and that critical point depends on the sampling distribution of this ratio under the conditions of the null hypothesis. And so again, it turns out that this ratio, when the null hypothesis is true, has an F distribution with, in this case, M minus P numerator degrees of freedom and N minus M denominator degrees of freedom. Okay, so here I've made the same modification to the slide to make it very clear that we're saying that this ratio follows an F distribution when the specified form of the model is correct. And so it's going to be this distribution, the F distribution with M minus P numerator degrees of freedom and N minus M denominator degrees of freedom, from which we would obtain the critical point for the lack of fit test in the case of, or in the context of, a multiple regression model. So for the multiple regression model case, we have the same set of hypotheses, the null hypothesis being that the specified form of the model is correct, against the alternative hypothesis that says that the specified form of the model is not correct. We have the same test statistic. The only difference here is that the critical point comes from the F distribution with M minus P numerator degrees of freedom and N minus M denominator degrees of freedom. And again, we have the same assumption upon which this test is based, that is, that the error terms have constant variance. It also has built into it an assumption that the error terms are normally distributed. Okay, so let's look at example 4.8, which shows how to apply this test. So this is example 4.8 from the textbook, testing for lack of fit of a regression model. And so this SAS program demonstrates how to test for lack of fit of a regression model using the data in example 4.8. And so there's a table there with a data set that you can input into SAS. I'll post this on Moodle so you'll be able to run this and check it out. I've gone ahead and input the data set here in the program itself. And so, well, we're going to do this. We're going to do several things here. We'll first test whether a simple linear regression model provides an adequate fit to the data, or if there's lack of fit. After that, we're going to add a quadratic term to the model and test whether this model provides an adequate fit to the data, or if there is still lack of fit. So we're going to test two models. We're going to look at two models. The first is a simple linear regression model that has just a single explanatory variable that is linearly related to the response variable y. We're then going to look at a multiple regression model where we have two explanatory variables, the same explanatory variable x as we had in the first model, but then we're also going to add the square of that explanatory variable. So it's a, in terms of x, it's a, we would call it a quadratic regression model. Now, the lack of fit test that we're going to perform is going to be accomplished in two ways. First, the lack of fit test, as shown in the textbook and in this lecture video, will be implemented in SAS using what we would call data step processing. All right, data step processing of the output from several SAS procedures. We'll then show how to easily obtain the lack of fit test directly from PROC reg. Now, one thing I want to point out, note that the text seems to indicate that the lack of fit test is only applicable to straight line, simple linear regression models. But that's not true, as we're going to see in this SAS program, where we apply the lack of fit test to a multiple regression model containing both a linear term as well as a quadratic term for the model. And it's also indicated, we showed in the lecture slides that we just covered that we can apply this lack of fit test to a multiple regression model. The one thing that becomes difficult in applying a lack of fit test to a multiple regression model is having data for which there are duplicates in the explanatory vector. All right, and so the more the problem is because the more explanatory variables you have, the less likely it becomes, unless you've designed the experiment in such a way that you have duplicates. If you're doing an observational study where you're sampling from a population, then as the number of explanatory variables increases, it becomes less and less likely that you're going to have two or more explanatory vectors with the same values for all variables. So the applicability of the lack of fit test becomes less and less as the number of explanatory variables increases. Okay, so let's take a look at the program. And so we have the data set here, and there's really no context provided in the example. We just have data. So the first thing we're going to do is print out a listing of the data set and take a look at a scatter plot of the data. So let me scroll back up here and run the program. Okay, so we have a listing of the data set. You can see we have 17 observations. We have an explanatory variable x, and we have a response variable y. And if we scan down the x column, you can see that we do have duplicates. So here is a plot of the data. And looking at this, the question is, would a straight line model fit this data well, or do we think that a quadratic model, a curved linear model, might fit better? And so it seems to me that in looking at this, it may very well be that a quadratic model would fit the data better than a linear or a straight line model. But what we're going to do is first fit a straight line model and then test that model for lack of fit. Okay, so we're going to fit a simple linear regression model using PROC reg. And I'm going to be using the ODS select statement to restrict the output so we can focus on what we want to focus on. And we're also going to save the output, or save to an output data set, the ANOVA table for the analysis. And then I'm going to do some further processing on that table, all right, to get values that I need to implement the lack of fit test. And so I'm not going to spend any time really. I'll let you read through the code. So let's go ahead and run this and see what we get. Okay, so we have the regression analysis. This is fitting the model. We're not testing for lack of fit yet. We're just fitting the model first. And I'm also printing out a residual plot. So we have the residuals on the vertical axis versus the predicted value on the horizontal axis. And if the straight line relationship was adequate, then we should see a random scattering of residuals about this horizontal line with no discernible trend. But I think you can see visually that there does appear to be a quadratic trend in the residuals. And so that would indicate to us that a quadratic X term in the model could be appropriate. But let's go ahead and see if that's confirmed by the lack of fit test. Okay, so we're going to continue on, and we're going to calculate the sum of squares for pure error, and also calculate the mean squares and so forth. And then we will, we're also going to calculate the F statistic and the p-value for the test. And so let's go ahead and do all of this in this, this section here. Okay, and let's see what we get. So that whole section implements the lack of fit test using data step processing on several SAS procedures that we use to get the values that we need for the test. And so the first thing I'm going to do here is I'm going to summarize the data by the values of X, by the unique values of X in the data set. There were 10 unique values of X, and at 5 of those, we had duplicates. All right, and then the rest of the results from the lack of fit test. Again, what I'm doing here is kind of rolling my own test, right? I'm using data step processing of output from SAS PROCs to get the values I needed to implement this test. And we can see here that based on these calculations, we have a sample size of 17. We have 10 distinct values of X, okay? And I copy that over into the variable M so that that corresponds to what we have in our notes. The sum of squares for pure error is 15.5630. The number of degrees of freedom associated with pure error is 7. The mean square for pure error is going to be the 15.5630 divided by 7. That gives us 2.22329. The sum of squares for lack of fit is 234.571. It has associated with it 8 degrees of freedom. We divide the sum of squares lack of fit by its degrees of freedom, the 234.571 divided by 8, to get the mean square for lack of fit, 29.3213. And then to get the F statistic, we divide the mean square for lack of fit, the 29.3213, by the mean square for pure error, 2.22329, and that gives us the F statistic for the test for lack of fit. Now remember that if in this case, the simple linear regression model is correct, then the mean square for pure error and the mean square for lack of fit are estimating the same quantity. On the other hand, if the straight line relationship is not adequate, if it's not correct, then the mean square for lack of fit is estimating something greater than that which is being estimated by the mean square for pure error. And so the mean square for lack of fit will tend to be larger and potentially much larger than the mean square for pure error. So that's why we're looking at that ratio. And you can see here that that ratio is 13.1883. 13.1883 is quite a bit bigger than 1. In fact, it's quite a ways out in the right tail of the reference distribution for this test, which is the F distribution with degrees of freedom given here. All right. And the p-value for this test turns out to be 0.001388715. So very small p-value. And so we can say that there is very strong evidence that there's lack of fit in this model. And so we would want to look at a more complex model to try to capture that variability. All right, next, what we're going to do is we're going to utilize the built-in capabilities of PROC-Reg to do this lack of fit test. And all we have to do is add the option lack fit to the model statement. All right, so it's very, very easy to obtain a lack of fit test using PROC-Reg. And so if we highlight that and run that, then you can see here in this output, and again, what I've noticed that I'm selecting just the ANOVA table to be output from this analysis, because that is where the information on the lack of fit test is going to be. And so you can see here that in addition to the row for the model in the ANOVA table and the row for error and the row for the corrected total, we have two additional rows, one for lack of fit and one for pure error. And you can see that the p-value for the lack of fit test is 0.0014. And if we round the p-value that we got to 4 decimal places, we get exactly the same thing. You can also compare the sum of squares for lack of fit that is produced by PROC Reg, 234.57080. If we round that to 3 decimal places, we would get 234.571, and that's exactly what we got in our calculation up here. The sum of squares for pure error, 15.56303. If we round that to 4 decimal places, we get 15.5630, and that is exactly what we got up here. And so the mean squares and the are going to be the same as well. So you can see here that we get exactly the same results, regardless of which of these two approaches we use, but clearly using the built-in capabilities of PROC Reg as it pertains to the lack of fit test is much, much easier than trying to program and then validate your own. Okay, the next thing we're going to do is we're going to because the lack of fit test is significant, and because that residual plot from the simple linear regression model seems to indicate that we need a quadratic term, we're going to go ahead and we're going to add a quadratic term to the model. Now, one difference between PROC Reg and, for example, PROC GLM or PROC Mixed, if you are familiar with those, is that we can't put in an X. We can't do this. Let me show you. We can't do that right there because PROC Reg is not going to recognize that. So we essentially have to, in a data step, create our own squared term. And so that's what I'm doing here. I'm just adding, I'm opening up for modification for updating this data set that contains the data. I'm calculating a derived variable that is the squared value of X. And then I'm going to invoke PROC Reg on that same data set and include not only X, but its squared value as well. And so that is what that's the model we're going to fit. And what I'm going to do first is I'm going to use this same procedure, all right, where we rolled our own, essentially, we implemented this lack of fit test using the data step processing. I'm going to do that. And so let's see what we get. So here we have the results of the analysis, and we're taking these results from the ANOVA table and from some other PROCs as well, and doing the calculations to implement the lack of fit test. And so again, we have 17 observations, we have 10 distinct values of X and so forth. And you'll notice here that the p-value for this lack of fit test is 0.18481. And so if we were using, for example, a 0.05 or a 0.10, even a 0.10, a larger significance level, we would not reject the null hypothesis in this case that a quadratic model is adequate. So again, the null hypothesis being tested here by this test is that the quadratic regression model is adequate for the data. The alternative being that it not adequate and perhaps even a higher order model would be needed. But we see here that at the significance levels that we would typically use, we would not reject the null hypothesis that the quadratic model is adequate. Okay, and then finally, we're going to ask PROC Reg to do that lack of fit test for us. Okay, and so you can see here that again, in the analysis of variance table, SAS has added, PROC Reg has added 2 lines, one for lack of fit, one for pure error, and the p-value for this test is 0.1848, which is the same value as what we got in our test. The F statistic 2.03, and if we round our F statistic to 2 decimal places, we would again get 2.03. And so we get the same value. All right, and so we can see here that it's very easy. Well, number one, we see that this lack of fit test applies to a multiple regression model. You know, it's not restricted just for a simple linear regression model, as the textbook seems to imply in the beginning of this section. All right, SAS is certainly willing to do this test for this multiple regression model. All right, we implemented it and it worked as well. And theoretically, there's no reason why it wouldn't work. Okay, and then if we look at the residual plot, we really don't see any trend in the residuals. And so visually, there doesn't seem to be any evidence of a lack of fit either. So that is how we can perform a lack of fit test in SAS. Again, there are a couple ways to do it in SAS. You could certainly take the time to program your own, but you know, if you're going to do that, you've got to validate it and so forth. Why not just use the capabilities that are built into PROC Reg? All right, it's going to be much quicker, much easier, safer from the standpoint of reliability. And but I did implement these using data step processing primarily to show you a couple things. Number one, you can you can do programming in SAS to implement things that are not that may not be built into SAS itself, in terms of options and things like that. But you know, when that capability is built in, it's probably best just to use that built-in capability, you know, for the sake of reliability as well as efficiency and get your work done. All right, so that's the end of this lecture video, and we will continue on with the next topic in the next lecture video.